Today we're going to be discussing the reality of gases, and that is that they are not ideal. They do not actually act in the way that we have been proposing so far in this class. The kinetic molecular theory assumes that no attractive or repulsive forces between gas molecules. And that's just straight up not true. We have to adjust our equation to get us closer to the true behavior of gases, because there are attractive and repulsive forces that gases undergo. And so if we want a better picture of what gases are really going to behave like in the world that we live in, we have to have a different equation. So this is that different equation. This is called the Vander Waals equation. And the Vander Waals equation introduces some new constants to our PV equals nRT, our ideal gas law. So we have two new things here. We have A and we have B. Now we're going to talk about A first. A is going to be our correction for intermolecular forces. This is my slight adjustment to the equation based off of those attractive and repulsive forces that the actual gas molecules are going to undergo. And we're not going to ever ask you to calculate for A. A is going to be a constant. It's going to be given for the particular gas, but you do need to be able to rank molecules for their largest intermolecular force based off of their formula giving you the Lewis dot structures. So what we're going to do first is we're going to draw or look at the Lewis dot structures for that particular molecule. If I give you the Lewis dot structures, sweet, you just have to look at them. If I don't and I just give you a formula, you're going to have to draw those Lewis dot structures first, and then you'll be able to see exactly which is going to be the largest for the intermolecular forces. We're going to be looking for that based off of something called symmetry. So symmetry is something that you should be familiar with. It's going to be how much the same one side looks to the other, whether that be top to bottom, left to right, some sort of diagonal. Okay, we're looking for it to look the same mirrored on both sides. My least symmetrical molecule is going to be the most polar molecule. Polarity means that I have an uneven distribution of electron sharing. And if I am not symmetrical, I am uneven and I will not evenly share my electrons. Therefore, I will be polar, and therefore I will have the largest A value. Polarity leads to slight or full charges on the actual molecules, which can then interact. If I have a positively charged or partially positively charged particle, it is going to interact differently with a particle that is also charged. Either in the same fashion where it is also positively charged, or a different one where it is negatively charged. It will act differently than if it came across something that was not charged at all. So that polarity needs to be taken into account, that A value. So we're going to look at two examples for what I could be ranking against. So I have the nitrogen molecule and I have ammonia here. Now what I'm going to look for is I'm going to look for symmetry. If I cut you in half, are you going to look the same on the left side and on the right side? For my nitrogen molecule, I'm going to look pretty much exactly the same on the left side and the right side. Whereas for my ammonia molecule, there's no real place that I can cut that will allow me to have the exact same things on both sides. So that would mean that my ammonia, or my NH3, is going to be less symmetrical, and therefore will be more polar, and will have a larger A value. So my ammonia will have the larger of the two A values. Now back up to talking about B. B is going to be the correction for my molecule size. Just like how you behave differently when you have gained or lost a lot of weight, you're not going to be able to move as fast potentially, or you'll be a little bit more forceful when you run into things because you're heavier. Molecule size matters as well. And so for B, we are going to really be able to kind of cheat here. The more elements that are present in that molecule, the larger my B is. Because therefore the larger the actual molecule is, the more people I have, the larger I am. If I have the same number of atoms between two compounds, I'm going to end up being larger if I am heavier. So I will also be looking for how much my molecule would weigh to determine if my B is going to be larger or smaller than anything in particular. So that's how we're going to rank A and B. And now I'm just going to go ahead and very quickly show you how I would actually utilize the Vander Waals equation for a calculation. So I have this initial question. So I have CO2 gas at 1 mole is going to be at a temperature of 373 Kelvin. And when that is true, it is going to be occupying 0.536 liters. Then it says, what is the calculated pressure using the Vander Waals equation? Okay, you have to be careful here. We're not always going to use the Vander Waals equation. Sometimes we might use ideal, but I will very specifically tell you that I'm looking for you to utilize the Vander Waals equation by either explicitly stating it, or when I give you equations for you to plug in, I'm going to give you the Vander Waals or ideal. And remember also for Vander Waals, we need the constants A and B to be defined. So I'm going to go ahead and I'm going to establish all of my givens. Now I know that my A value and my B value were not explicitly stated in the problem, but they will most likely be pulled out and stated sort of in this fashion here. So we have our A value, our B value, our N value, our T value, our V value, and then good old ideal gas law constant. This is going to make a reappearance here. Once I have my givens established, I can go ahead and state that my unknown is going to be that pressure. It says, what is the calculated pressure? So that means I am going to be looking for the pressure. I am then going to take my Vander Waals equation, which is this. Inside of parentheses, I have P plus A N squared over V squared, in parentheses, open parentheses, V minus NB, close parentheses, is equal to nRT. This is a big long equation where I need to solve for P. So what I'm going to do is I'm going to divide both sides by this parenthesis set, V minus NB. And that will open up these parentheses, leaving me the accessibility to remove this value here, A N squared over V squared. And I just have to subtract that from both sides to end up with this equation here. So like I said, this was going to be divided out. So I have it here with my division, and then I'm going to be subtracting, since I have to undo that addition, that A N squared over V squared. Once I have my new equation, I can go ahead and substitute in my actual values. Here we do need to be very, very careful that we are utilizing parentheses and we are specifically squaring the things that need to be squared and not the things that do not need to be squared. So this specifically, forgot that little end parenthesis there. I have the square only going to the 0.536 and the 1 here. I am very careful to not let it apply to anything else. After I've gone through and I have multiplied everything out and I've divided everything out, the number that you will end up getting will be that my pressure is going to be equal to 49.525,60038. And whenever I round to that first decimal, 2 doesn't make me round up, so that 5 will be left alone and all the other numbers will drop away. And I will have atmospheres left as my only unit. And that's how you're going to deal with the Vander Waals equation.